Not started. So, we will start discussing today about a very important aspect of embedded system design, that is power aware systems. Let me or the system measures that can be taken for low power. All right. Now, there is a now there are two things that we are concerned about. One is power. All of you know what electric power is, right? And another factor is energy. And you know that they are related. Energy is the integral of power over time, right? Now, both of these are important. So, therefore, three things are important. One is the power, and one is the energy, and the power and energy are related by the time for which you use it. So, if you are doing net surfing on your mobile for a long time, then more power will drain out. Now, net surfing doing on your mobile is at your intention, maybe at your will, but there are some programs which are taking more time to run. Therefore, they will affect the time component, and for the same power more energy will be drained. So, why are we concerned about power? Power as such will affect the design of the power supply, right? How to design the power supply, all right. It will also be determined by the interconnects, their dimensions. If there be, depending on the interconnect dimensions and the way they are drawn, more power may be consumed, all right. Energy, on the other hand, is an integral of power. Therefore, we will also be concerned about the computation time. So, we want to minimize both of them, right. Now, we will see in today's lecture and maybe a sequence, through a sequence, how we can approach the management of power, because power is becoming all the more important for embedded devices which are portable and mostly run on batteries, and the battery lives are very important. Okay. Even when we go for say Mars expedition or wherever spacecrafts, we have got the power supplies and they have got a life. So, we have to enhance that life. So, our objective is to study power on energy aware embedded systems, dynamic voltage scheduling. There are two approaches, dynamic voltage scheduling and dynamic power management, by which we can approach solving this problem, or at least try to solve this problem. Okay. There is a very interesting picture here, that so much heat is generated in a Pentium processor that you have got a egg poach here, right. So, you do not really need a kitchen. You can put your egg on the heat sink and you can get your breakfast ready, right. So, next let us come to the fundamentals of power consumption of a gate. Where from does it come? So, let us have a little look at the circuitry without going into the intricacies. We have got a supply voltage and we have a couple of transistors. Okay. And this is negated, and there is another one and we are giving the input at this point. All right. This is a transistor. So, from here we have got some current that is flowing even when the transistor is off, that is the leakage current. I write it as ILK, the leakage current, right. Whenever this transistor is on, then there is a short circuit current, that is the current is flowing through this, right. And across this transistor I have got some load through a diode, and from here I can take a capacitor, sorry, and that is the actual load and we connect to the ground. So, that is the CL, the capacitive load. Now, whenever we are making excursions in this circuit, the excursion is between 1 and 0. So, whenever we are switching from 0 to 1, say this transistor, then we are having a switching current flowing through here. So, that is, it can be either way, it will be switching current. So, we have got three components. One is ILK, which is the leakage current, which is there all the time. Okay. There is a short circuit current, we do not have much to do with that, and the other is the switching current. Right. More the switching activity in a circuit, the more will be the power consumption. Okay. So, this is the basic circuit behind any component of an embedded system. If we assume that, then we can come to a couple of equations. Say, we can write that power can be expressed as alpha, which is a coefficient denoting the switching activity, the load capacitance that we have shown here, the load, as much as the load increases, the power consumption will increase, we have to drive more. The load impedance, the other component is the supply voltage, and it varies as a square of the supply voltage times the frequency at which we run it. So, what are the things? Alpha is the switching activity, CL is the load capacitance, VDD is the supply voltage, and F is the clock frequency. This is a very important equation that we will have to remember. So, this tells us a couple of things. This tells us that if we increase the circuit switching, then power consumption will increase. It also tells us this CL, but the CL is basically this is a hardware component. So, whenever we design it, if we can reduce the CL part, then obviously P will be reduced. The supply voltage, now we will have a lot of things later on coming, where we can play with the supply voltage and the frequency. Okay. Now, the supply voltage and the frequency are also related. Okay. Now, this is one parameter, the power, and we can see that the power increases consumption, power consumption increases quadratically with the VDD. And there is another thing which is the delay, let us call it tau, delay of switching in a CMOS circuit. This is nothing but a CMOS circuit. Right. So, the delay of switching delay in a CMOS circuit can be given as some constant k times the load capacitance times VDD divided by VDD minus V, let me call it T. T is a threshold square. That is, beyond this voltage nothing will happen, no switching will take place. So, here again Vt is the threshold voltage, that is dependent on the device design. And actually Vt is much less than VDD. So, what we observe from here is that while the power is quadratically related to the VDD, it increases quadratically as the supply voltage increases. Here the delay is increasing or decreasing, is inversely proportional linearly, okay, approximately linearly. So, decreasing the VDD will reduce, if I decrease the VDD, it will reduce the power quadratically, if I reduce this part. If I reduce this part, then delay will increase, and as the delay will increase, that is causing an impediment to the frequency at which I can drive the circuit. That is actually determining the frequency. So, this f and this tau are therefore very closely related, right. So, now for energy optimization, let me keep this slide on and say P is alpha, whatever we had, that I did not write that again here, but energy is alpha CL VDD square F into T, where T is the time, T is the time. Okay. Now, if I look at this component F times T, F is number of cycles per second and T is the time. Therefore, I can conveniently write it as, let me write it here, alpha CL VDD square, number of cycles, right. Now, this gives us a lot of insight here. One thing is, we will play with VDD a lot, but you can see a number of things coming up here, which we will take up in detail later. So, number of cycles a program will, embedded program will take to run will be dependent on what? Complexity of the instructions, the number of instructions that are there in the machine level. Who determines that? Number of instructions that will be there at the machine level, the compiler. So, given a task, an efficient compiler will generate an efficient code, whereas an inefficient compiler will generate an inefficient code. Therefore, depending on that my number of cycles will vary, and that will be affecting energy. So, you see the energy, the battery life is not only dependent on hardware, but it is also dependent on compiler, and we will see how it is also related to operating systems. Okay. Now, again alpha, it is a switching the switching frequency, right. Now, if I have, just giving you an insight, if I have 1111 to be one instruction, and immediately after that I have the next instruction is 0001, there is situation 1, and the situation 1 is another one is 1111, and I have got 0111 as the next instruction. In which case is there more switching? In the first case, I have to switch between each of them, whereas here I have to switch between only one. Now, where is this switching taking place actually? It is taking place on the bus, wherever we am transmitting, there also this switching is taking place. So, corresponding the bus will be actually a number of components, right. So, at every component that switching is taking place, so this alpha is becoming higher. Therefore, if we can quickly say that if the Hamming distance can be minimized between the consecutive instructions, probably alpha will reduce, but that is a very one angle to look at that, but there are many other issues. So, when we design the machine code, that is also very important, but we never know which instruction will come after what. So, but you can probably over a large segment of codes you can try to make some estimates, but so those are number of interesting issues are coming out over here, right. So, saving energy under a given how can I save energy under a given timing constraint? I have to take some time. Okay. We can reduce VDD, we can reduce the switching activity, we can reduce the CL, or we can reduce the number of cycles. One thing is that I take less cycles, okay, thereby we can gain. So, assuming that this part is clear, we can look at a slide here. You see, let us keep this also side by side, and let us look at this. What does this slide say? Again taken from Professor Peter Marvidal with his permission. Now, you can see this green one is showing the increase in frequency, right, the clock frequency and the VDD. Here we can see that as we increase the VDD, that means I am referring to this, I am referring to this equation. This is pertaining to this equation, right. So, it is increasing linearly, this one. As the VDD is increasing, the maximum, the delay is inversely proportional to the frequency, right. So, that you have to understand that. So, the frequency, the moral of this is what, that if I give higher VDD, I can probably operate this thing at a higher frequency. On the other hand, as I increase the VDD, and if I look at this axis, on this axis, which is energy per cycle in nanojoule, it is increasing quadratically more or less. Okay. So, here at 2.5 volt I am consuming 10 nanojoule, whereas at 5 VDD I am consuming 40 nanojoule. All right. So, there are two aspects of the thing. One is, depending on the VDD, I am also constrained to the maximum frequency up to which I can go. If I can increase the frequency, my thing will be solved faster, but that may not always be the case. So, that is the challenge. First of all, let us try to realize the challenge, and then we will look at the solutions. Now, how can we handle this? So, once again let me quickly revise this part. So, this part tells me that the power or the over time energy will increase in the square of VDD, whereas here I find that the delay will be linearly, will be inversely proportional. So, the frequency will be linearly proportional to the VDD. As I increase the VDD, I will get more and more frequency. Now, the frequency is important because as the frequency increases, my energy consumption is increasing. So, all these are interrelated. So, how can we manage this? One thing that we can think of is spatial and dynamic supply voltage management. All the parts of the circuit need not be given a uniform VDD, the same VDD. We can have, say for example, this part is a very busy module and this is a hotspot. Most of the computations are being done here in the red one. So, I want to make it faster. So, I put it at 3.3 volt and 200 megahertz. Now, if I go from this sort of curve, I can say that at a particular frequency, at a particular VDD, what is the frequency that I can get. So, here I can have at 3.3 volt I can run it at 200 megahertz, whereas this one is a standard one, not that busy. I run it at 1.8 volt, which allows me to run it at 100 megahertz. So, I am slowing it down, I am reducing the VDD also, but I ultimately need to see for most of the embedded systems it can be a real time, there may be a real time constraint. So, we have to meet the deadline, right. So, I can do a mix and match of my allocations of VDDs, so that I can meet the deadline, at the same time I consume less power. So, and for the slow module, you see I have put 1.3 volt and a much lower frequency 50 megahertz. In another, there is a 3 level, it can be also, there are 2 modes, a busy mode and there may be a normal mode. Okay. So, depending on what is the performance, here the performance is reduced, therefore, this part, this module I do not need any longer. Okay. So, that sort of thing takes place. The analogy for this is the biological blood supply systems, right, different supply to different regions depending on the activity, whichever parts are more active, and whenever you increase the activity at a particular point, then the more and more blood supply goes there. So, accordingly you can adapt your policies and do that, right. So, here is another example to illustrate this thing. That is a transmitter, is a processor, and for a particular benchmark what is being shown is, you can see that if we look at the power, initially we are running it at 300 megahertz. Why? We can see that the system is idle, it is a sleep mode here, and here comes a request, user hits a mouse button. So, some process has been activated. So, immediately you can see the frequency, I have changed the frequency to 800 megahertz. Okay. So, I am adapting the frequency. Now, here the task runs, this task that was initiated at this point runs and finishes here, right. It cannot be shown here right now. And then it returns to the sleep mode. Again, here might be something has started. Here at this point, user starts a DVD movie. Immediately it shoots up. Now, just in the earlier slide I had shown that the performance requirement is not the same all the time. So, when the DVD started, you needed to start the DVD and all those, you needed more power. Therefore, at that point I shot it up at 1 gigahertz. All right. So, then later on when it is stabilized, then I can come to much lesser frequencies, frequencies adjusted to the necessary level to sustain the application, and that is going in a steady state, right. And then ultimately it comes, DVD finishes and I go back to the sleep mode. So, in that way we can change the frequency. So, it is not necessary that when you have got a 1 gigahertz processor, that means all the operations. If all the operations are done at 1 gigahertz, a huge amount of power will be consumed. So, that is automatically adjusted. Now, ideally we can think of a processor for the sake of power management to have a power supply which I can continually change. Suppose I had a VDD box here, a power supply box. Or the VDD. Some VDD comes out of this. It would be ideal if I could continuously control it, if it were linearly controllable for every point, but that is practically not very feasible to have such continual supply. For that, most of the systems that we have will have some discrete levels of, say, maybe 3 levels of power supply. Okay. 3 levels of power supply, say 5 levels, whatever. So, here we can switch between any of these levels and we can get the VDD. Okay. Say it can be, this one is 5 volt, this one is 4 volt and this one may be 2.5 volt. All right. So, if we assume that sort of scenario, then let us assume this, that we are working in a scenario where VDD, I will vary, there are 3 possible VDDs. One is 5 volt, 4.0 volt and 2.5 volt, all these are volts. And by the equations that we have shown, we can have energy per cycle and we can have the F max in hertz, the maximum frequency that we can run, and we can have the cycle time. Once again, coming back to this here. So, we are playing with the VDD and depending on the VDD, we will have some frequency component and so consequently, we will have the cycle time and cycle time is the inverse and we will have the energy per cycle. Okay. So, as you know that we can have, say, at this we have got 50, this is megahertz, I am sorry, frequencies in megahertz. So, it can be 50, 40 and 25 megahertz. By the characteristics I found that these are the values. So, the energy per cycle here we found is 40 nanojoule, for this it is 25 nanojoule and for this is 10 nanojoule. And the cycle time therefore, this is 20 right in nanosecond, (20 nanosecond, 25 nanosecond and 40 nanosecond. Now, we have got that. So, I have got this choice. I have got this choice, right, that I can run it at 5 volt, I can run it at 4 volt, I can run it at 2.5. And consequently, corresponding to each of them, I will have so much energy consumed per cycle. This is the maximum frequency at which I can run it, etc. Now, I am given a task has been given that requires requires 10 to the power 9 cycles to be run within 25 seconds. So, my deadline is 25 seconds. So, I am given a scenario where I have to run the task within, say this is 25 and say this is 20. My scaling is wrong. So, this should be 15, this should be 10, this should be 5 and the scaling is right, okay, somehow. So, these are the different, this is time in second, this time in second, right. Now, if I have to run 10 to the power 9 cycles. So, if I run it at 5 volt, say here it is so this is 2.5 volt. So, maybe this is 4 volt. So, this is 5 volt. If I run it at 5 volt, can you tell me how much time it will take to complete? 10 to the power 9 cycles, and I am running it at 5 volt. So, 20 nanoseconds per cycle. So, it will be over by 20 seconds, right, although my deadline was 25 seconds. So, I have run it at 5 volt and I could finish it off within this time. So, the energy consumed is this, I will be getting from here. So, this is the energy consumed is actually will come from not from this is the task area. VDD taken 5 volt, I will compute some energy here. How much will that be? Okay, 40 per cycle, and I took 10 to the power 9 cycles. So, my energy consumption will be 10 to the power 9 cycles, every time it is 40 nanojoule, right. Energy was in nanojoule, this was I did not write, this was in nanojoule. I am sorry, the energy given here is in nanojoule. So, it will be 10 to the power minus 9. So, that will be 40 joule. So, I am consuming 40 joule of power, 40 joule of energy by running it at 5 volt, but was it necessary? If I had, I mean, since I can run it at a frequency of 50 megahertz, I could finish it much earlier, which I need not do. If your constraint is that you have to finish the job as early as possible, in that case certainly you can reduce it, right. But otherwise, I had the scope of reducing it. So, let us try to do that. With the same distribution, if I take the same distribution remaining here, all right, as earlier. If I had scheduled it in a different way, I'm sorry. If I had scheduled it here, say I run it at 5 volt for 15 nanoseconds. For 15 nanosecond I run it at 5 volt, and then for the remaining 20, 25 nanosecond, here is 25. My criteria was to complete it within 25 seconds, right. If that be the case, that here I run it for 2.5 volt and here I run it for till 15, I run it for 15 seconds, I run it like this. What will be my energy consumption? What will be my energy consumption? I have run 750 megacycles at 50 hertz. 50 means 50 hertz, 5 volt means 50 hertz. So, I have run actually 750 megacycles here. I mean 750 million cycles. So, I am sorry, whenever we see capital M we say mega. 750 million cycles we have run at 50 hertz, and only 250 million cycles at, this is at 50 hertz. Because of this, at 5 volt I could run it here, and this much at 25 hertz megahertz. Oh, sorry, 50 megahertz and 25 megahertz. So, my energy consumption will now be 750 into 10 to the power 6 into 40 per nanosecond, this per cycle, right, into 10 to the power minus 9 plus 250 into 10 to the power 6 into 10 into 10 to the power minus 9. So, that will come to 32.5 joule. What did we get earlier? We got 40 joule earlier. Now, the last option, another option we take. So, by this we get 32.5. Now, if I keep this again here and just run the whole thing at 4 volts, there is 2.5, there is 4 and there is 5. So, instead of running it at 2.5 the whole thing for 25 seconds, I run it at 4 volts, right. Then how many cycles am I expending at 4 volt for 25? 4 volt gives you 40 is the frequency. How many cycles have you spent? You need 10 to the power 9 cycles. So, all the 10 to the power 9 cycles at 40 megahertz, right. What will be the energy consumption? Let us compute that again here. It will be 10 to the power 9 times 25 and 10 to the power minus 9. So, that will be 25 joule. So, you see, for the same task I had 3 possible voltages, 5, 4 and 2.5. So, by adjusting, by combining into them, I can get different energy consumptions. One was 40 joule, one was 32.5 joule, another is 25 joule. Okay. Okay, stop here and we will carry on with some algorithms which can be used to find out what would be the optimal one. 5 minutes break. Break.